Okay, hi pre-cal, BC1. So the first thing I want to do right now, this first part of the screencast is just me talking. Again, hopefully what you are coming into this screencast having done is you've Desmosed um, that little investigation, right? I had you look at those functions in your Algebra 2 textbook, and I asked you to see if you made any connections, okay? And so I asked you, what did you notice? And I gave you a question here: if f of x equals sine x and g of x equals 3 sine x, how does the graph of g of x differ from f of x? And you probably saw that, when you Desmosed it, the amplitude of g of x was 3 due to the vertical stretch of f of x by a factor of 3, right? And then you maybe looked at, what about the graph of f of x equals cos x and g of x equals cos x plus 7? You notice that g of x is f of x shifted up 7 units, okay? And you also Desmosed functions that looked like this and looked like this, and you probably saw that the period was affected when the argument of the sine, okay, was multiplied by something, and you probably saw there was some horizontal shift when a transformation like this occurred. And tomorrow in class, we have our long period. I'm going to show you and talk to you about a very efficient way to make sense of and sketch these graphs when you have multiple transformations going on. But just for now, my expectation of you now is that you Desmosed what I asked you to Desmos over the weekend, and you just observed some relationships, all right? So that is the extent of what my expectation is of you right this second. All right. Now the rest of this pencast is going to be on functions and their inverse. All right. And I should tell you too, the homework from this assignment is going to be in your calculus textbook. Okay. You all bought the calculus textbook for class. It's the one with the funky green, squares on the front. So the homework for this, which is due tomorrow, is going to be from that textbook. So first, let's talk about functions and their inverse. Let's give you some notation. We're talking about functions. Functions means f of x. And then a function's inverse. That's this notation. Okay? Notice, very important, this notation, see the superscript of -1? That is not treated as an exponent. Okay, not to be confused with this, please, ladies and gentlemen, where it's f of x to the power of -1. This would equal 1 over f of x, okay? But the inverse of function f, that is this notation right over here. Okay, so when we talk about functions and their inverse, there are a couple of different vantage points, and I know we've talked about different perspectives, okay? There are several different perspectives that one could take when it comes to looking at a function and its inverse. So the first thing I'm going to do here is I'm going to go ahead, okay, and I'm going to sketch this curve here. Okay, this here is the function. I'll call this f of x equals, it's the square root function shifted left 2 and up 2. So it's the square root of x plus 2 plus 2. Okay, that is the function f of x. And I'm going to do this. I'm going to label just some points here, might as well. This is 2, 4. Okay? Okay, first I'm going to talk about a function and the inverse of a function. I'm going to talk about the inverse of a function from a graphical perspective. All right? From a graphical perspective, the inverse of f of x, okay, so here's the first kind of point I'm going to make about inverses. The inverse of f is a reflection of f of x over the line y equals x. So graphically speaking, if we had the graph of function f, the inverse of f is a reflection of f of x over the line y equals x. Well, all I'm going to do here is with reasonable accuracy, I'm going to graph the line y equals x, okay? Reasonable accuracy here, reasonable accuracy. And if I reflect f over the inverse of f, and if we were doing this together in class, maybe I would use like some transparent tracing paper, we'd fold the paper. But basically, what you would see is that -2, 2 would become the point 2, -2. -1, 3 becomes the point 3, -1. Hi, Tyler. Okay, 2, 4 becomes this point. And what you may notice is that, okay, this here is the graph of the inverse. And if you want to do a little exercise, you can go ahead and, graph f of x. Use some graph paper, graph f of x, graph the line y equals x, fold your paper along the line y equals x, and see where f of x lands, and that would be the inverse. So this is the inverse, okay? You'll notice that the inverse of a function, if you look at corresponding points, let me just take a look here for a second. What is the relationship between x, y on f and the corresponding point on the inverse? And there is the second little feature. xy becomes yx, right? So the x coordinate of f becomes the y coordinate of the inverse of f, and the y coordinate of f becomes the x coordinate of the inverse of f. That's what this notation means, okay? xy becomes yx, all right? You'll also notice something else, ladies and gentlemen. Not only can I say the x coordinate becomes the y coordinate and the y coordinate becomes the x coordinate, basically the roles of x and y kind of swap as well. So if I look at f of x for a minute, and I ask you for the domain of f of x, you would say the domain here is the set of x values that are greater than or equal to -2. And the range is the set of y values that are greater than or equal to +2. But if I asked you for the domain and range of the inverse of f, let's see, domain of the inverse of f, you would notice that you would say the x values are bigger than or equal to 2, and the range, y values, are bigger than or equal to -2. And right again, here you see that what was true of x on the function is true of y on the inverse. And what was true of y on the function is true of x on the inverse. Okay, so the inverse of a function is, some people like to say, the inverse of a function is the roles of x and y swapped. And I understand what they're saying. And I think if when you say that to yourself, this is what you're thinking, then I'm okay with that. Okay, yes, the roles of x and y do swap. Okay. Here in this example, I want to ask you a question. For this example, or I should say for this f of x, and this f of x was the square root of x plus 2 plus 2, okay? I'm going to say that f of x is something called 1 to 1, okay? Or invertible, okay? What does it mean for a function f of x to be 1 to 1 or invertible? A function is 1 to 1 or invertible if its reflection over the line y equals x is also a function of x, okay? So, which means the reflection of f of x over the line y equals x is also a function of x. So let me give you an example of a function that is not one-to-one or invertible. All right, here's an example of one. Reasonable accuracy. Reasonable accuracy. Let's go ahead and graph the graph of y equals x squared. Okay, this is the graph of f of x equals x squared. If I took these points and I reflected over the line y equals x, and here I'm not going to draw on the line y equals x, but let's see. If I take this entire function, and f of x is a function because it passes the vertical line test, here's what I get. Okay, and you will notice, I hope, that the inverse here is not a function. The inverse is not a function. So here, notice that the reflection of f of x over y equals x is not a function of x. Okay, so f of x is called not one-to-one or not invertible. Okay, notice if a function is not invertible, notice here I did not use this notation. I didn't say, look, here is the inverse of f. You want to know why? Because when you use this notation, it is understood that the inverse that you're looking at is a function. So this is actually, there's some assumptions going on when you use that inverse notation, okay? Now I could say this. I could ask you this question, boys and girls. You know what, and it's so funny. My husband heard me doing a screencast, and he said, when you say boys and girls, it sounds like you're talking to an elementary school. And I said, why? And he said, I don't know why. I don't know, it does. And I guess it does. Like I say, boys and girls, put your chocolate donuts away. But you are boys and girls. And I mean, if I say guys does not include girls. So anyway, I'm going to ask you this question, ladies and gentlemen. Is there a way that you could restrict the domain of f of x so that f of x is one-to-one? In other words, could you tell me a segment of the domain of f of x that would make it one-to-one? Okay, pause me and think about it, and then replay me. Okay, the answer is yes. Maybe I would say, if I look at f of x only over the interval of its domain where x is bigger than or equal to 0, then that would yield this portion of the curve. And that part is invertible. That part is one-to-one because the inverse of that yellow part would be right here. Okay. Alternatively, I could also say, what about looking over f of x over the interval of x less than or equal to 0? That's also valid because that would be this portion. Okay. And that portion reflected over the line y equals x would be here. Okay, so sometimes people will ask you, or a text or Ms. Yam will say, f of x here is not one-to-one, but is there an interval of its domain over which the function is one-to-one? All right, and here there would be two different possible answers. Okay, so here's a question for you. I'd love to see what you are able to glean. Give me the features of the function of f of x that would make it one-to-one. Tell me what features of f of x make it one-to-one. What features of f of x make it invertible? Okay. What features of f of x allow for its reflection over the line y equals x to also be a function? Think about it, come up with a conclusion, then replay me. Okay, well, the answer is, If f of x passes, not the vertical line test, but if f of x passes the horizontal line test, then it is invertible. So what does that mean? Well, you know that when you look at a function, okay, when you are given a function and someone says to you, is this a function of x? Does this describe y as a function of x? You apply the vertical line test, right? You scan it vertically to see and ensure that the vertical line doesn't hit the curve more than once. Well, you can also apply a horizontal line test. If a function passes the horizontal line test, it is one-to-one, which means if you run a horizontal line down a function and it never intersects the curve more than once, then it is invertible. Okay, so that's one thing that you could think about. All right, so now let's do this. Let's talk about the last feature of inverse functions. Let's take this from like a graphical perspective. Okay, so point 3. Once found, oh wait, that doesn't make any sense. Good grief. Okay, this is the last feature of functions in their inverse. F of the inverse of f will always equal the inverse of f composed with f, and these will always equal x. Okay, so let's see what I'm talking about. Okay, so the first two characteristics are kind of graphical characteristics, all right? The third is an algebraic characteristic. But to really appreciate this one, you probably first have to ask yourself, like, well, how do you find the inverse of f given f of x, right? How do you find it? Well, I will show you. All right, so let's say you have this. Let's say you have f of x equals, okay, let's see. Okay, let's do this. Let's say it equals, oh goodness, what curves could we do? All right, let's do this one. The cube root of x minus 6. And I'm asking you to find the inverse function, right? Algebraically, like I'm not asking you to sketch this. I'm asking you actually to find the inverse. Okay, here's what you do. The first thing you do is, sometimes it helps. Okay, I'm almost done. Y equals the cube root of x minus 6, okay? When you're finding the inverse, the first thing you do is you swap the role of x and y. So x equals cube root of y minus 6. Now, once you've swapped the x and y, solve for y. Cube both sides. X cubed plus 6 will equal y. Once you have solved for y, boys and girls, this is the inverse function. So the inverse is equal to x cubed plus 6. Okay? My battery is running low. I'm going to show you the composition, this feature 3 tomorrow in class, okay? But this is how you find the inverse. Oh my gosh. Okay, it's running very low. Okay, I have to stop.